Thank you very much for the invitation and for organization of this conference. My name is Milena Ratajczak. I'm an assistant professor working at the Astronomical Observatory, University of Warsaw. So I'm a researcher, astronomer, but I'm also involved in many space-related education activities, many outreach things related to astronomy and also space. And I try to converge these two things, and I hope my talk will be actually telling you about it, how I'm trying to do it. But before I will go to that, I would like to tell you how the life of astronomer look like, and actually how the life of observer look like, and how it has changed over the last years. So in tens of years ago, we were using big telescopes, so-called reflectors. Actually, we know telescopes since Galileo, and we've been using lenses in telescopes, and we call them reflectors. And that's the one that you can see on the left-hand side on the top of the screen. But at some point, we decided that we have to change a bit the path of a light that the telescope will gather, and we started to use mirrors. And on the second image, you can see actually a refractor, so the one that uses mirrors. And it's not so long telescope, and it has bigger mirror than the lens that was at the first image. And then we started to send telescopes into space. And on the right-hand side, you can see the James Webb Telescope, space telescope. That's the biggest telescope that we've sent to space. So, and if you look at the bottom of this slide, you can see the comparison of the Earth-based telescope. So the James Webb Telescope, the biggest space telescope, has a diameter 6.5 meters of a mirror. And the telescopes that you can see on down here, these are Earth telescopes, so the one that are based on ground. And actually, the smallest of them is 8 meters. So the one to the left side, they are VLT, very large telescopes, 4 telescopes and a diameter of 8 meters. Then the 3 biggest ones are the one that don't exist yet. So the second one is extremely large telescope. It's being built in Chile. It belongs to European Southern Observatory. Its diameter is going to be almost 40 meters. And then we have telescopes of about 10 meters. These are Keck telescope that are in Hawaii. 30-meter telescope that is being under construction, another 10 meters telescopes, and the giant Magellan telescope. So the third big one is still under construction. So we can see the biggest telescope right now here are 10 meters, and we are building 40 meters mirror telescope. So why do we go into bigger mirrors? Is because we want to see more. So we want to go deeper with our observations. So with all of these techniques that I described right now, so changing the optics of the light that comes by sending telescopes to space and by making their mirrors bigger, actually we get more data. But that's not the only thing that astronomers need. Apart from having big mirror, we need to observe big fields of view. So it's not that, like in the old days, we were observing only one star and we were actually drawing it or having them at the photographic plates. Later on, we started to use photomultipliers. Later on, CCD cameras, but there's also field of view. So the field that we can see with one telescope. And down here, you can see the full moon. So the size of the full moon to the comparison of what this square degrees that I'm showing you right now mean. So actually you can see the biggest field of view that we have right now at ZTF. It's ZTF telescope. It has 47 square degree field of view. But look at the other telescopes here. We are building LSST right now. It's going to start its operation in next year or in 2 years. But please take a look at the SDSS. SDSS is the one on the left side, because I'm going to get back into that. So big field of view means more objects can be observed. SDSS is a Sloan Digital Sky Survey. It's a 2.5 meter telescope. It's a robotic telescope. You can see it on the left side. It has a special design camera, and the image from it more or less looks like the third one that you can see on the slide. And every dot at the screen is actually a galaxy. If you zoom into it, you can see the one that you have on the right side. It's one of the galaxies. But actually, it turned out that one of the researchers working on SDSS, when he was early researcher in his early stages of career, he was given a task to classify 1 million of these galaxies. And you can see they can look very beautiful, like the one that the zoo of the galaxies that you can see on the left-hand side. But sometimes they are really blurry and you don't really know what they are. And he classified 50,000 per week and so on, so on. And he was so bored and so disappointed with all the effort that he has to put that he thought that, wow, why cannot we give this data to people? These are just images. They are not so difficult to say. And the only thing that they were about to do is to say if the galaxy is more spiral or more elliptical, or it has some special features. And that's how he designed the citizen science project called Galaxy Zoo. Citizen science means that we give the science to citizens, to passionate individuals who don't really have the training in astronomy. So the citizen scientists were given the image, like the one on the right side, and the question, is the galaxy simply smooth and rounded with no sign of disk? And they have to say if it's smooth, if it has features or disk, or if it's something like bad zoom, or they don't really know. And the project called Galaxy Zoo gathered around 500,000 people, volunteers, who started to classify these galaxies, to look at the images from SDSS and classifying that. And that was a big success. And that's how the Zooniverse idea was created. Zooniverse is a web platform, is a browser platform where you can actually apply any kind of citizen science project in terms of that you're giving the data, you're giving a tutorial, you say what the volunteers have to do, and they do it. And as you can see, the Zooniverse has a logo very similar to the Galaxy Zoo, so to the galaxy. So it really started with astronomical projects. And nowadays, you can find thousands of projects at Zooniverse. It's called people-powered research because these are scientific data and these are analyzed by people. So you can, for example, work on nature, animals, biology, like Snapshot Serengeti. It's a project that you actually look at the photos, the images taken by the cameras that are in Tanzania, in the national parks, and you actually say what kind of animals you see there. There's also historical ones like ancient lives, when you actually look and try to check the signs from the papyrus from Egypt, and you try to translate this signs. And one of my favorite ones is Wales FM, and it's actually, you don't look into images, you don't look into signs, but you actually listen to sounds, and you try to distinguish in between the sounds of whales that are in the ocean and background sounds. So that's really super cool, and Zooniverse really helps into doing that. So since we are in a Life and Space conference, I wanted to tell you a bit more about citizen science projects that are related to exoplanet search. So you probably are aware of the Kepler space satellite. Kepler was working in space for almost 10 years, observing one fixed field of stars. And it was its main goal was to find exoplanets via transit technique. And it's more than 2,600 planets confirmed from Kepler. But there are still data that has to be analyzed because it's not so obvious. So when you have an obvious case, for example, the one on the left-hand side, you have a star and you have a planet that is transiting. So it's going around the star. That's a simplification, of course. And you see the brightness of the star is going down because of the eclipse by the planet. But if it's more complex, if it's not just one planet, if it's another object, you have a Santa here, for example, then these changes of the brightness that you observe are more complex and more challenging. And you don't really know if it's an exoplanet or is it a star or is it something else. And the data that are given to the scientists, to the citizen scientists, are not images of the star, but these are just data points. So on the right-hand side, you see the plot showing the brightness of a given star that is observed by Kepler satellites over time. So you see at some point, you see the changes, like a drop of the brightness, and that's most likely the transit. Obviously, this is an easy case, and actually you can use algorithms and machine learning to actually teach your algorithm to do so. But many of these cases are more complex and are not so easy, and you really need human eye to spot some kind of difference. I will get back into that in a moment as well. Another interesting object is Rosetta Zoo. You probably know Rosetta mission, so the one that was going to 67P comet and landing on it, but also orbiting around it. And these photos are all taken by the Rosetta mission, showing how active the nuclei, the cometary nuclei was. And what our citizen scientists given in this project are actually images from the orbiter. And in the bottom, you see the changes in between, like it's 10 or even 9 months, the difference. And you see there's a big stone that actually is like 30 meters in a diameter that was moved by more than 100 meters. So these are the differences that not only are easy to find by the algorithms, and sometimes are really found by people. So this is another project. And the one project that I'm involved in, it actually involves the Gaia space mission. Gaia is a European Space Agency mission that actually scans the entire sky. So it's a telescope, but it doesn't look at the one point as a one field of view as a Kepler telescope did, but it actually observes with its 2 telescopes the entire sky. Its main idea is to create the most accurate 3-dimensional map of our galaxy, because we don't only measure brightness, but we also measure the position, velocity, temperature, composition of almost 2 billion objects. So we actually have not only the 3D map of our galaxy, but it's a guide. So with every point, every source, we have all this set of information. But what I'm most interested in as an astronomer in the Gaia data, Gaia gives us hundreds of gigabytes of data per day. So there's a lot of data. And what we get only here on ground are not images, are just points. And with these points, we see if the sources that we observe, by sources I mean either star or a galaxy or even an asteroid, do they change, do they vary in time? So we have detected around 10 millions of variable stars that we classified into 24 types using machine learning. So by variable stars, I mean, for example, pulsating stars. These are stars that changes their brightness because they change their size. And if they change their size, they also change their brightness that you can see on the left plot here. Another idea of the variable star, another example, are eclipsing binaries. So these are actually not only one star, but 2 stars that eclipse each other. And with the brightness changes, you can actually see 2 dips that tells you when one star eclipses each other. And obviously, the classic case that we already talked about are exoplanets. So transiting exoplanets are also kind of variable stars because we observe the variability of a star. So we see the changes of the brightness, not only brightness in the terms of Gaia, but that's the main plot I would like you to tell. So we've started this Gaia Vari project. Gaia Variables project is a citizen science project that helps us to classify things, because the idea is that we put already classified data there. The plot here, it's the plot that you can get going into Zooniverse. It looks a bit complex, but for those of you who are somehow interested in astronomy, you can spot the so-called light curve, so the changes of the brightness of a given star, its position at the color magnitude diagram, its position in a galaxy. It's not important to go into details right now, but by looking at the shapes of the changes, for example, here, you can say if a star is an eclipsing one, if it's a pulsating one, like a Cepheid star, if it's a Lyra Cepheid eclipse pulsating star, or long period variable. So there is a tutorial telling you what you have to do, what you have to look at, and so on. But why do we need it? Because as I earlier mentioned, that we have machine learning that does it, but we won't find the most exciting case in machine learning. Machine learning is great for finding things that we want to find, that we know what to find. But we sometimes have stars or sources that are outside these all classifications, and those are very often the most interesting. Another idea that is behind this project is that we really need a very, very pure sample to teach our algorithms towards the next Gaia data release. So we really want to have, because it turned out that a lot of, for example, Cepheids that we classified with machine learning, it turned out not to be Cepheids. So we have to revise our algorithm. And there are many of these already scientific results that we found by having this project that is for half a year already on. So with this short video, short video, I would like to invite you to join Gaia projects and all the citizen science projects related to astronomy, but not only, because science is very often powered by people like all of us. Thank you very much.